So in this video, we're going to talk about solving rational inequalities. And remember that solving rational inequality is very similar to solving a polynomial inequality. And the easy way to solve these is to actually look at the graph. And when we look at this graph, the rational inequalities, when we want a polynomial, we want to know when the graph is either above zero, below zero, or actually at zero. So what you're doing in a polynomial inequality, you look at the zeros of the function. Well, rationals have the same concept. You're looking for the zeros of the function, but you're also going to look at other values that are going to cross that x-axis. And in particular, you're looking at your undefined values. And those come by looking at the denominator. So remember, a rational function is any kind of function that can be written in the form f of x is equal to some kind of numerator, n of x divided by d of x. And so for this, we're actually interested in three things. We're interested in the zeros, which come from the numerator, n of x. We're interested in the undefined values, which come from the denominator, d of x. And we're also interested in our wholes, which we may or may not get, but remember we get wholes from dividing the numerator by the denominator, looking at any cancel terms. So when we deal with this, we're going to look at a function such as this function to the right over here. And you can look at this function and see where f of x is greater than 0 or f of x is less than 0. And it's greater than 0 when it's above that at x-axis. So here we see that every place that it says above, f of x is greater than 0. And every place that it is below the y-axis, we know that f of x is less than 0. So all it's really saying is where are the values either above or below that x-axis. All right. And when we write these out, we're going to write them in interval notation, using our interval notation. So for instance, if I want to know all the places where it was above 0 at, I see that the first section where it's above 0 is from this point right here to this point over here. And looking at just the x values, that's the that's the x value that sits here at that vertical asymptote and here at the origin. So we go from the first place that is above 0. It's from, we're not going to include vertical asymptotes, remember. So we go from -4 to 0. And we're going to include the 0 there because that's part of the function. There's a second place that we have above 0. We need to remember we're covering that gap there with the union. And it's from here at another vertical asymptote. So we're going from, remember we don't include vertical asymptotes, 3. And then it goes all the way this way to the right. So that's to positive infinity. So there are all your intervals where it's going to be positive or above 0. The negative intervals go from, well, it's coming all the way from the left like this on this side over here. And we don't include negative infinity, so it's negative infinity. And again, you're at this vertical asymptote, you're stopping, you won't include it. So we're going to go up to -4, but we won't include it. Then we have a gap, union, and then we go from 0, and again, we're going to include that 0 because it's part of the function. And it goes all the way up to this vertical asymptote again, not including it, so that is 3. So when we look at our graph, we can actually see that the values that are included in here are going to be x-intercepts, any kind of, here's an x-intercept by the way, any kind of undefined values, such as vertical asymptotes or wholes. All right, so that's what we're going to look at in this next part. So now that we've looked at the graph, let's actually look at an example of how to solve this algebraically. And by algebraically, what we need to do is look at 3 things. We need to see if we can find any zeros, any wholes, and vertical asymptotes. So when I look at this, remember to find the wholes, I have to factor this. And because we're looking at the equation x plus 3 over x minus 4 is greater than 0, right? There's no factoring that really needs to be done. So there's not going to be any wholes here. To find our zeros, we want to find the zero of a rational function. The first thing we do is we set the top equal to 0. So x plus 3 is equal to 0, which means that x equals negative 3. So my first 0 is going to be negative 3. It's only a 0 I'm going to get here. Then I'm going to look at the undefined parts, or the asymptotes, the vertical asymptote. To get this vertical asymptote, set the bottom, the denominator equal to 0. So x minus 4, remember, does not equal 0. So x cannot equal positive 4. And what I do now is I draw a number line. And on that number line, I'm going to put any holes, vertical asymptotes, or zeros. And so here I just have the value negative 3 and the value 4. And the way this works is that because we have holes and because we have zeros and asymptotes, at a 0, you're going to put a closed circle because it can equal that number. But at a asymptote, you're going to put an open circle because we know we can't equal that. And we're going to section off our number line into parts now. And each part means that the graph is changing within that part. So what we want to find out is if the graph above 0 or is it below 0. And to do that, all we do is we take our equation, x plus 3 times x plus 3 over x minus 4, and we're really only interested in our signs. And what I mean is we're going to pick a number on the left-hand side of negative 3. And we generally want to pick something pretty big because it's going to help us identify what this value is. And so I'm going to evaluate the function at a number that's less than, or on the left-hand side, negative 3. I'm going to evaluate the function at f of negative 10. And when I plug in negative 10 into the equation, here's what I get. I get negative 10 plus 3. I really don't even care about the number, but I do care about the sign. So when I plug in negative 10 into this x right here, I get negative 10 plus 3, which is the negative 7. And all I'm going to do is write the sign. So that top part is going to be negative. The bottom, I plug in negative 10 minus 4, I get another negative. So it's a negative over negative, the signs. And when I look at that overall, that's going to be a positive. So that means within that particular interval, anything less than negative 3 will be a positive value, or the graph will be above the x-axis. I do the same thing here. Pick a value between negative 3 and 4. An easy value to pick there is going to be the value of 0. So if I evaluate f of 0, 0 plus 3 is positive. 0 minus 4 is negative. So now I'm dividing a positive by a negative, and I get a negative sign there. So everything there is below. And then the last one, I'm going to pick a value greater than 4, and I'll do f of 10 again. 10 plus 3 is positive. 10 minus 4 is also positive. So everything in this interval is also going to be positive. And so now here's what I'm interested in. I'm interested in anything that is greater than, which means that it's above, or it has to be positive. So I'm interested in my positive signs. So here and here. And so when I look at this now, I can write the actual solution using interval notation is going from, on the left-hand side, that arrow means negative infinity, up to negative 3. And because there is no equal to this part right here, we won't include the actual 0. So we'll just do it in parentheses. And then we have a gap from here to here because there's negative in this interval right here. So after that, though, we use a union to cover the gap. And we'll go from this vertical asymptote, which will never be included, regardless if there was an equal sign here or not. Because it's an asymptote, you can't include it. It goes from 4 to positive infinity. And here's your solution. So on this example, let's actually go through the process again. And remember, we're trying to find zeros, holes, and vertical asymptotes. And so the first thing we're going to do is this equation we can factor. So the top factors into x minus 2, x plus 2. And then the bottom factors into x minus 2 times x minus 3. And that's less than or equal to 0. And notice here, you have a hole at x minus 2, but they both cancel. So you're left with the reduced or the simplified form of the rational function to be x plus 2 over x minus 3 is less than or equal to 0. And so when we look at this now, we have a First off, we have a hole. Our hole is at x minus 2 equals 0, or x equals 2. Then we have a 0. Let's find our zeros next. The 0, remember, set the top equal to 0. And you're going to set the reduced or simplified form equal to 0. So I get x plus 2 equals 0, or x equals negative 2. And then the last thing I'm going to find is going to be my vertical asymptote. And so that'll be just x minus 3 equals 0, or x equals 3. And so now what I'm going to do, remember, I draw my number line, and I put all those values on my number line. So I have negative 2, which is a 0, and I can include the zeros. I have positive 2, which is a hole. Don't include your hole. And I also have positive 3, which is an asymptote. Don't include the asymptote. So we're going to section off our graph into parts again like this. And we're going to test inside of each interval. So the first one I'll test at is f of a number less than negative 2, f of negative 10. And again, this time when I plug in, I'm going to plug it into the simplified form. You can plug it in either part, actually, but you plug it in simplified, it makes the math a lot easier. So negative 10 plus 2 is a negative. Negative 10 minus 3 is a negative. So this is going to be a positive in that interval. Next interval, a number between negative 2 and 2. Well, let's do 0. Plug in 0. 0 plus 2 is a positive. 0 minus 3 is a negative. So that interval has to be negative. In between 2 and 3. So I'm going to pick a value like 2.5. So I'll do f of 2.5 inside of here. And f of 2.5 is going to be, when I plug that in, 2.5 plus 2 is going to be a positive. 2.5 minus 3, though, is going to be a negative. So inside of that interval is also going to be negative. And then within the last interval, I'll pick a value that is bigger than 3. So let's do f of 10. 10 plus 2, positive. 10 plus 3, positive. So inside of that interval is positive. So now I can see that the intervals I'm looking at, or the intervals I'm interested in, are my negative, my below intervals. I want my below. And so those below intervals occur from here at negative 2 up to 2. And remember, because we have a hole here, we have to cover that with a union. And we go from 2 to 3. So we're going to write this as, we include it now because it's equal to. So we'll include the negative 2 up to 2. But we can't include that positive 2 because it has a hole at it. And so we'll use this, and then we'll cover that hole using the union, and we'll go from 2, don't include it again, up to 3, but we don't include that again because it also has it's an asymptote, so we're not going to include that. So here's the final solution.